Dear students, today we are going to discuss the remaining part of the AASHTO rigid pavement design method, and mainly we will focus on the joints. Joints are purposefully placed discontinuities in a rigid pavement surface course. All types of joints are used in rigid pavement construction methods for all PCC pavement types. CRCP, continuously reinforced concrete pavement, uses longitudinal reinforcing steel in order to limit the number of transverse contraction joints, but it still uses longitudinal joints and periodic transverse joints. So if you just look at the joint types, mainly we are having these types: contraction joint, expansion, construction, longitudinal. As far as the joint geometry is concerned, in that case you will have to look at the spacing, the layout of the joint, and the dimensions. And one important thing, which is the joint sealant dimension. That is very, very important. Well, if you look at the types of the joints again, contraction joint. Contraction joint is a transverse joint for relief of tensile stresses. Well, the contraction joint is a sawed, formed or tooled groove in a concrete slab that creates a weakened vertical plane. It regulates the location of the cracking caused by dimensional changes in the slab. Unregulated cracks can grow and result in an unacceptably rough surface, as well as water infiltration into the base, subbase, and subgrade, which can enable other types of pavement distress. Contraction joints are the most common type of joint in concrete pavements. Thus, the generic term joint generally refers to a contraction joint. Contraction joints are chiefly defined by their spacing and their method of load transfer. They are generally between 1/4 to 1/3 times the depth of the slab and typically spaced every 12 to 50 feet, with thinner slabs having shorter spacing. In some countries in some countries it is quite common to use a semi-random joint spacing pattern to minimize their resonant effect on vehicles. The transverse contraction joints can be cut at right angles to the direction of traffic flow, or at an angle called a skewed joint. Skewed joints are cut at obtuse angles to the direction of traffic flow to help with load transfer. If the joint is properly skewed, the left wheel of each axle will cross onto the leaf slab first and only one wheel will cross the joint at a time, which results in lower load transfer stresses. Well, if you just look at the expansion joint, again the transverse joint, and transverse expansion joints are provided for relief of compressive stresses, and used primarily between pavement and structures, for example, bridges. So for the expansion joint, we can say that an expansion joint is placed at a specific location to allow the pavement to expand without damaging adjacent structures or the pavement itself. Up until the 1950s, it was common practice in the United States to use plain jointed slabs with both contraction and expansion joints. However, expansion joints are not typically used today because their progressive closure tends to cause contraction joints to progressively open. Progressive or even large seasonal contraction joint openings cause a loss of load, particularly so for joints without double bars. Okay, then comes the construction joint. Well, a construction joint is a joint between slabs that results when concrete is placed at different times. This type of joint can be further broken down into transverse and longitudinal construction joints. Then comes the longitudinal joint, and the longitudinal joints are provided for relief of curling and warping stresses. Warping stresses mean the twisting stresses because of the twisting. There is another type of the joint which is known as the isolated joint. An isolated joint is used to lessen compressive stresses that develop at T and unsymmetrical intersections, ramps, bridges, building foundations, drainage inlets, manholes, and anywhere differential movement between the pavement and a structure may take place. They are typically filled with a joint filler material to prevent water and dirt infiltration. Now, here on this particular slide, you can see the typical contraction joint details. So there are different types of contraction joint. You can see the dummy groove. So you can see that this is the joint, and here a seal has been placed, a seal with plastic material. If the total thickness or the depth of the slab is small h, so we are having this filling of seal up to h by 4 to h by 3. In some handbooks you would find symbol D for the depth of the slab. So both either small h or capital D for the depth of the slab or the thickness of the concrete slab. Now here you can see again the dummy groove, but here the lubricated smooth double bar has been placed at the mid depth. Now look at this one, that is the pre-mold strip. Now here, after having the joint, after cutting the joint over here, felt or asphalt ribbon or asphalt board strip has been inserted at the top, and again you can see that this insertion is from h by 4 to h by 3. This pre-mold strip type of contraction joint is without double bar, but here you can see that the double bar has been placed at the mid of the slab. Now on this particular slide you can see the typical expansion joint. So you can see we are having this smooth lubricated double bar. This is basically the joint, and you can see that expansion cap has been placed over here, and here seal with plastic material is present. So this is the typical you can say the expansion joint. On this particular slide, you can see the typical construction joint detail. Now, this type of joint is called as the butt joint at contraction joint, and this is the key joint for emergency. So look at that. We are having this cut, I mean to say the joint, and a smooth lubricated dowel bar has been placed at the mid depth. And here, this is the first slab, and this is the next slab, and we are having the connection with that first slab in this manner. Look at that. So a key has been generated over here. So that's why it is called as the key joint. Now, on this particular slide, you can see the typical longitudinal joint. Well, keep this thing in the mind that tie bars are used in longitudinal joint, whereas dowel bars are provided in the transfer joint. Now, look at the longitudinal joint, dummy groove, ribbon or pre-mold strip, deformed plate. So look at that. Here we are having the joint, deformed bar has been placed, and at the top we are having the sealant. Now here you can see the ribbon or pre-molded strip has been placed at the top, and you can see the deformed bar is present at the mid depth. And here, this is the deformed plate type longitudinal joint. Here special steel plate is inserted at the joint, and you can see that the deformed bar is present again at the mid depth. So these are some typical types of the longitudinal joint. On this particular slide, you can see lane at a time construction. So here you can see some sort of key has been generated at the joint. So you can see here the slope 1:4, and you can see that for the first slab we are having this shape, and this is the next slab. The shape is like that, and this distance is 0.2 times of h. And again you can see the deformed steel bar which has been placed at the mid. Well, joint spacing. Joint spacing is very, very important whenever you are going to consider the joints. So local experience is the best guide, or we can follow the rules of thumb that in the case of jointed concrete pavement, joint spacing in feet is less than or equal to 2 times D, and here D is the depth of the concrete, thickness of the concrete slab in inches. W over L is less than or equal to 1.25. The meaning of this is that the width of the panel of the slab divided by the length of the slab panel, it should be less than 1.25. Or you can say the ratio between W and L should not be greater than 1.25. Joint dimensions. Width controlled by joint sealant extension, and the depth in contraction joints D by 4 and in longitudinal joint D by 3. Joints may be formed by sawing, inserts, forming. Well, sawing is just like a special cutting tool is used to develop the joint in the concrete slab. Inserts are the special arrangement which are placed in the concrete slab to generate the joint, and the forming means the proper formwork is provided to develop the joint. So if you just look at the formation of the joints, so we can say that mainly we are having the two types, or you can say that Joints can be formed in two ways generally. Contraction joints are most often sawed in after PCC placement. Others such as expansion, isolation and construction joints are created by form work before the PCC is placed. Each one of these methods of joint construction has its own method and set of consideration. Okay, now on this particular slide you would find some information about the sealing of the joints. Before sealing, the joint is required to be cleaned of all foreign materials. This is done by water blasting, sand blasting, mechanical wire brushing, or a combination thereof. Care is taken not to damage the joint when cleaning. All residue of the sawing operation is required to be removed from the joint face for proper sealant adhesion. A quick test for cleanliness may be made by inserting a small clean object into the joint. If residue or dust is retained on the object, additional cleaning is required. Once the joint has been thoroughly cleaned, the backer rod, a tool, may be installed if required and the sealer may be placed. All joints are to be sealed prior to discontinuing work for the construction season or before opening the pavement to public traffic. Construction traffic may be allowed upon the pavement prior to this sealing process. Now on this particular slide you can see the joint sealant dimension which is governed by the expected joint movement sealant resilience. So this is the formula here. This delta L is basically the joint dimension, or you can say the joint opening caused by temperature changes and drying shrinkage of PCC in inches. Here in the formula, S is the allowable strain of joint sealant material. Most current sealants are designed to withstand strains of 25 to 35%. Thus 25% may be used as a conservative value. Alpha sub C, the thermal coefficient of contraction of Portland cement concrete per Fahrenheit. Z, the drying shrinkage coefficient of the PCC slab, which can be neglected for a resealing project. L, the joint spacing in inches, and here D, capital T sub D, or even you can say delta capital T sub D, that is the temperature range that we are considering in Fahrenheit, and C is the adjustment factor due to subbase or slab friction restraint. Use 0.65 for stabilized subbase, 0.80 for granular base. So with the help of this formula, the joint sealant dimension can be determined. Now on this particular slide you can see the design inputs Z and alpha sub C, and for that we can use this table 2.9 for Z, and for alpha sub C this table can be used. So you can see that corresponding to indirect tensile strength in PSI we are having this shrinkage coefficient value, and here corresponding to different type of coarse aggregates we are having the concrete thermal coefficient per Fahrenheit from this table. Now on this particular slide you can see the reinforcement design for JRCP. JRCP, you know, jointed reinforced concrete pavement. So look at that. This is the longitudinal joint and this is the transverse. This is the transverse joint. So at the transverse joint we are having the dowel bars and on the longitudinal joint we are having the tie bars. As this is JRCP, jointed reinforced concrete pavement, so you can see the reinforcement steel is provided. The distributed steel or the wire mesh fabric is provided in the panel. Purpose of reinforcement is not to prevent cracking, but to hold tightly, close any cracks that may form. Physical mechanisms which are involved, the thermal contraction and the friction resistance from underlying material. Design based on friction stress analysis. On this particular slide, you can see the double bars, transfer joint load transfer. Size and spacing should be determined by the local agency's procedure and or experience. General guidelines are that double bar diameter is D by 8, where the D is the thickness of the concrete slab. Double spacing minimum 12 inches, double length minimum 18 inches. Well, look at this nomograph. With the help of this nomograph, we would be able to carry out the reinforcement design for jointed reinforced concrete pavement. Either we can use this formula, that is P sub S, just to determine the steel which is needed. P sub S is equal to L multiplied by F divided by 2 divided by Fs into 100. So if you just look at this nomograph, it can be applied to both longitudinal and transverse steel reinforcement. Generally, the steel percentage is 0 when L is less than or equal to 15 feet. But it is always advisable to use some steel at the joint. Well, if you just look at this nomograph, well, this bar is representing the slab length L in feet. Well, this one is the friction factor F. This is the turning line, and you can see that this bar is meant for the percent steel reinforcement required, that is capital PS, and this bar is meant for steel working stress F sub S, that is in KSF. Now look at this example. In this example you can see that the length, slab length, that is equal to 36 feet. F is 1.5 and F sub S is 30,000 psi. So either by using this formula or by using this nomograph, you could be able to get this P sub S. Let's see how can we do it. So slab length is this much, so we are here. Friction factor is this one, so just draw this line and just reach here on the turning line. Now look at the steel working stress which is given, that is 30,000 psi, so it means 30 ksi, so this is 30. So from this point, join this point like this, so this will obviously pass through a certain point on this bar, and you can read the percentage of steel from here, and it is coming equal to 0.085%. So in this way, you know, we have determined the percentage of steel. Well, this slide is showing the friction factor table corresponding to different types of material beneath slab. So in this way you can get the friction factor. This slide is meant for steel working stress, number 4, number 5, number 6 bars, and indirect tensile strength of the concrete at 28-day strengths are mentioned over here, and so we can get the allowable steel working stress in KSI from this particular table. Now there is one footnote which is written for DWF proportional adjustments may be made using the wire diameter to bar diameter. Well, this DWF stands for distributed wire fabric. I will repeat, DWF, it stands for distributed wire fabric. So this table is based on preventing fracture and limiting permanent deformation. Now if you just look at this particular slide, transverse tie bars. Now the title of this figure is recommended maximum tie bar spacing for PCC pavements assuming half-inch diameter tie bar, grade 40 steel and subgrade friction factor of 1.5. Now there is one example which is given. You can see in this example the distance from the free edge is equal to 24 feet and the thickness of the concrete slab is 10 inches. And if you just look at this figure, this axis is representing the maximum tie bar spacing in inches, and the horizontal axis the distance to closest free edge in feet. So in this example you can see 24 feet. So just corresponding to just going upward, and just look at this curve. These curves are meant for different slab thicknesses. So just go up to the 10 inches, and then in this way you can see that this is coming equal to 16 inches. Now there is one important note which is written at the top. Look at that spacing greater than 48 inches not recommended. Now if you just look at this particular figure, again it is meant for transverse tie bar, but look at the title, recommended maximum tie bar spacing for PCC pavement assuming 5 by 8 inch diameter tie bars, grade 40 steel and subgrade friction of 1.5. Now look at this example. Distance from free edge 24 feet, D is again 10 inches. So using this figure here, look at that, this is 24 feet, so corresponding to that, just looking at the 10 inches, the concrete slab thickness, so you can see here 24 inches. So as you can see in this case, the diameter of the tie bar is more, so you are having, I mean to say the diameter is more than the previous example which was on the last slide. So you can see that here the spacing has been increased. Again the same note is written at the top that the spacing greater than 48 inches not recommended. So in this way we have completed this topic, design of rigid pavement as per AASHTO guidelines. Now at the end of this while you would find some examples. You will have to solve these examples yourself. We have already discussed all important things in this topic. So solve these examples. So this is the first example, this is the second and the third.